Welcome folks, we're gonna do a new tutorial on how to use LTSPICE where we're gonna simulate a first order RC circuit, and we are interested in the frequency response, the step response, and the sine wave response, which is the response when we apply a sine wave signal where we use phasor analysis to solve for the circuit. So let's get started. So the first thing I'm gonna do is I'm gonna load LTSPICE. So I load LTSPICE here, then I'm gonna create a new schematic, and now I'm gonna build the circuit, and I'm gonna start with what we call the AC analysis. And the AC analysis in SPICE and LTSPICE means that it is frequency response, which means that we're gonna vary the frequency and we're gonna see what's the gain going to be or what's the out going to be as a function of frequency. So I will start with the resistor. Here is my resistor. I'm gonna rotate it 90 degrees, then flip it, and then I'm gonna add a capacitor. Here is my capacitor. Remember that to once you place the capacitor or the resistor, to exit the drawing mode, you just click on escape. Escape will make you do that. And now I wanted to add an independent voltage source, so I'm gonna click on component and I'm gonna type here voltage, and then I see it highlighted here, so I'm gonna click on it, and that's basically all what I need. It's a simple RC circuit here. And now what I need to do is I need to define the value for this resistor. So I'm gonna make it 1K. Keep in mind that K here is a multiplier, is what we call unit prefix. No space in between. 1K, no space. If you have a space, it's gonna be a syntax error. Then for the capacitor, I'm gonna make it 1 micro. 1U stands for 1 micro in LTSPICE. And then for the voltage source, I have to specify it to be AC voltage source, which what we call the small signal analysis. Is basically gonna be an AC sweep kind of analysis. So I right click on the voltage source. I'm going to go to advance. Over here I see small signal AC analysis. That's the AC analysis. So I'm gonna give it a value of 10 volts here. The phase is gonna be 0, so I will keep it as is. There is no resistances, no DC value, it's only frequency response here I'm looking at. Those are for the transient, the time analysis. I'm not gonna use any of those either. So that's it. Then I'm gonna say okay, and I can basically move this over here to make it look nicer. I can change the voltage, the name of this voltage source. I will come right on the top of the name. I will right click on it and I will call it VI or VN. So that's the input voltage. Then I'm gonna basically have a wire and I will draw the rest of the circuit. When you draw the circuits, try to be as neat as possible. It helps that if the drawing circuit will look very similar to the circuit that you're trying to simulate, the drawing in the circuit you're trying to simulate. So try to make it very similar to what you have in your assignment. Now what I'm gonna do is I stepped out, so I'm gonna click on OK, and then I'm gonna come to this one where it says zoom full extent. I can use the wheel in my mouse to zoom out a little bit, so I'm gonna zoom out a little bit. I can move it by right clicking on the panel, that drawing panel, and I can move it right and forth. So now the circuit is completed, almost. I need to add the ground here. You must have a ground in every SPICE circuit, right? So if you're gonna come in and you're gonna say that I'm gonna save, I like to do save as. So I will save it as default is draft, but I can call it like video 1. For example, to know that this is for tutorial video. And now I can go to view and I will look at SPICE netlist, And you can see that there is a text file. This text file here basically describes this particular circuit. Basically, the netlist will say that what components are connected between the nodes. You always have the ground node going to be the 0 node that you see over here. And then this node over here is N001. And this node over here is N002. So it tells you that what component is connected between the nodes. This is called the netlist. This is the old way of describing the circuit in SPICE. But now we use circuit schematic to describe the circuit, which is much easier to follow, as you know. It's good to know that because it gives you some understanding of what's going on. Now what we're going to do is we're going to basically simulate the circuit. So I'm going to simulate the circuit. I'll come to simulate, edit simulation command. Now we're going to run AC analysis. So this is, if this is your first time doing AC analysis, pay attention to what I'm going to do here. There's different kinds of sweep. Sweep means vary, like, you know, you sweep in the frequency means you vary in the frequency from some initial value to some final value. So here we're going to select the sweep to be a decade. That's the best way to do a frequency response, but you can use octave or linear. Then here, because remember that SPICE, LTSPICE, use numerical methods, right? It's a numerical technique, it's algorithm. So we need to define how many iteration points, how many points to be evaluated in each decade. So here I will write 1,000. The higher the number of iteration, the higher the resolution, the better or the more accurate your analysis is going to be. Then what you're going to do is you're going to say that what's the start frequency here. So I'm going to start from 1 Hertz. So I can write 1 like that, or I can do it 1 Hertz, no space. And then I'm going to stop at 1 meg. So meg going to be, I can use it as capital M small eg, or you can do it as capital M eg. And when you write meg, it's going to be those 3 letters MEG. However, if you forget and you write capital M, because most textbooks will use capital M for meg, if you forget, it's going to also be a syntax error. So make sure that it's MEG stands for meg. And SPICE is case insensitive, so you can make it capital letters or small letters. So this is a command. Basically, this is the command. We call it a command. This command requests SPICE to do AC sweep. And if you go back to, once I save the file, if you go back to view netlist, you will see that this command here is stated in the netlist. So this is the command that will tell BSPICE to run the simulation. So this is the circuit. Now we are going to simulate the circuit. So I'm going to click on run, and now I want to plot the gain. The gain gonna be V out, which is this node, over VN, which is this node. So the way I'm gonna do it is I'm gonna click on V out, and this is not the gain, this is V out. Before I even go into the graph here, to find the gain, I'm gonna come on the top of node 002. I will right click on it, and I know that this here is the expression, the algebraic expression. To find the gain, I have to divide by the input voltage, which is VN001. So it's basically saying that find the voltage VN2, divide by the voltage VN1. Now this is the gain. So now what you need to do is you need to see the graph carefully. So you can see that the vertical axis on the left will give us the gain in dB, and the vertical axis on the right will tell us what's the phase in degrees, and the horizontal axis is the frequency. It has given us the frequency in hertz, and it is a log scale. It's a log scale. So the interval from 1 hertz to 10 hertz is called decade, and the interval from 10 hertz to 100 hertz called decade, and so on. And you can see it's a log scale. So for example, if this was 100 here, this mark gonna be the 200, this mark over here gonna be the 300, this mark here gonna be the 400, all the way to 900 over here, then 1000. And you can see that as you get closer to the end of the decade, right, the intervals get crowded, or the ticks will get crowded, which means that it will take smaller amount to reach to the next integer value of that decade. What's important here is that the gain gonna be 0 dB at low frequencies, and then eventually at some corner frequency, somewhere around here, it will start to drop linearly, right? So we call it, the slope here is gonna be negative 20 dB per decade. So if you're gonna go from here to here, or let's say that if you're gonna go from here to here, you're gonna lose 20 dB. It's called negative 20 dB per decade. That's extremely important. So, and then we are interested in something we call the corner frequency, is the frequency at which the gain gonna be 3 dB below the DC gain. Because this is low pass filter, it has a gain of 0 dB or a gain of 1 at low frequency, and then it's gonna drop to negative 3 dB at some frequency. This frequency is called the corner frequency. So to find the corner frequency, I'm gonna use the cursor. I'm gonna come over here and I'm gonna click on it with my mouse. And this is called the cursor. So, and then I can move the cursor until I hit the negative 3 dB. So I'm gonna move the cursor here, and I need to read that the magnitude over here gonna be negative 3 dB. At the negative 3 frequency, at the negative 3 dB frequency, the phase here gonna be negative 45 degrees. So I think this is good enough. So you can see that the negative 3 dB frequency in the simulation occurred at 159.53 hertz. Now in theory, if you solve for the 3 dB frequency here, it is going to be in radian per second, it's going to be the reciprocal of the time constant. So the time constant here going to be 1 millisecond. It's basically R times C. So 1K times 1 micro going to give me 1 millisecond. Take the reciprocal of that, will tell me what's the corner frequency in radian per second. So that's going to be 1000 radian per second. That's the corner frequency. But you need to convert it to hertz, so you divide by 2 pi. So in theory, it should be 159.155 hertz. Very close to this value. So there is accuracy in the algorithm itself, and there is also accuracy in the precision of the machine itself, the computer itself. So the computer will have a precision, a finite precision. Also the algorithm that runs the iterations will have also another precision. But this is pretty good. I would assume that this corner frequency is really good in the simulation. It is very close to the theoretical value that we are expecting. If you go a decade later, you're going to see that roughly the gain going to be negative 20 dB, because it's going to lose 20 dB per decade. So if I come over here until I hit 1059, very close here, right? I have supposed to be 1590. I have 1600, very close. So you can see that the gain is roughly around 20 dB, right? It loses 20 dB per decade after that. If you go a decade later, so around 15,900, yeah, that's good. So you lose another 20 dB, you get negative 40 dB. Right? So here, what we did is the AC sweep basically showed you what's the gain gonna be as a function of frequency, by increasing the frequency for this particular circuit, the gain will drop. Now keep in mind that this makes sense, because if you're going to use the analysis of the impedance, we know that the impedance of the capacitor varies with frequency. So the impedance of the capacitor will be 1 over j omega c. So at very low frequency, if omega is very low, if the frequency is very low, the impedance is very high here. Then because the impedance is very high here, most of the voltage sent from the input will be captured by the capacitor, right, using the voltage divider concept. However, at high frequencies, the impedance of the capacitor becomes smaller. That means most of the voltage will be across the resistor. Smaller voltage will be across the capacitor. It makes sense. It's a low pass filter. So, and this is the first aspect of this circuit that we're going to do. Now what I'm going to do is I want it to relate to step response of the first order RC circuit. So I'm going to basically delete this AC sweep, because we're going to use transient response. So what I'm going to do here is I'm going to click on cut. I will delete, select this here. I don't need that first. Let's max here. And I'm going to basically click on cut, delete this, and then I'll do skip. Now I'm going to come on the top of the voltage source, and I'm going to change it. Now I'm going to apply a pulse signal. So I'm going to say that the voltage is going to start from 0 to 10. So this is going to be a rectangular pulse. And I'm going to say that it's going to change from 0 to 10 at t equals 0. And then because LTSPICE uses numerical methods to solve for circuits, you can't jump from 0 to 10 in 0 seconds. So we have to say that it's going to jump from 0 to 10 very fast. So I'll use very small value compared to the time constant. I know the time constant here is 1 milli, so I will use 1 nano. So it's going to jump very quick from 0 to 10. And time fall going to be 1 nano. And then the on time here is the width pulse. So I know that the time constant is 1 millisecond. And to reach the final value, usually you're going to say that it's 5 times tau. So it's going to be 5 milliseconds. But I'm going to go a little bit higher. So I would say that I will use like 8 milliseconds. That's my T on. And then the period going to repeat every 16 milliseconds. And I will keep it running forever. So here what I did is I said that the voltage basically gonna jump from 0 to 10 in 1 nanosecond, and this gonna last for 8 milliseconds. Then it is gonna jump back to 0 within 1 nanosecond, and that will stay for another 8 milliseconds. And I will show you the shape of the input signal when we run the simulation. So what we did here is we end up defining the input voltage as a function of time. So that's what I have for V pulse. I'm gonna move it so that we can see it. I move it over here, then I'm gonna zoom out. So that's what I have for the circuit. Now I need to define the simulation again. So before I simulate the circuit, I will come in here. Now I'm going to do transient because this is time domain. So I wanted to show 2 complete cycles. So here I have 16 milliseconds per cycle. So I'm going to do that 32 milliseconds. That's complete cycle, 2 complete cycles. I will start saving the data immediately. And then here, this is very important step, which is basically the maximum step size. So here we're looking at the time between 2 sampling points, between 2 points step size, right? That's step time, right? Between 2 sampling points. So you want to make it very small, but the smaller you make it, the longer time it will take to simulate the circuit. So usually what you want to do is you're going to say that, you know, I would choose a good value to be around 1,000 samples per cycle. 1,000 samples per cycle. I know that each cycle here is around 16 milliseconds. So I would say like 10 micro sounds good. I can even go a little bit lower. I would say 1 micro, right? That means it's a higher resolution, right? So here I will say that I will have 1 micro is the maximum step size. So this is not a fixed step size. It's basically changing step size, and the algorithm itself will predict what's the next step size going to be, but it can't go any higher than 1 micro. So the algorithm is a little bit smart when it runs the simulation, right? It will decide what's the next step size gonna be, right? And then based on that, it will evaluate the next sampling point. But it is adaptive. It can't go any larger than 1 micro. So I'm gonna enter that. Again, this is a command. Now it says tran, means that run transient analysis. Again, this here and this here will be entered into the netlist. So if you save this file and then we go to view SPICE netlist, now you can see that VN has changed, right, to describe the bulls, rectangular bulls, and the tran to represent the transient command. So now we're gonna run the simulation, and what I'm interested in here first is I wanted to graph what's VN is. So you can see that VN will jump from 0 to 10 at 0 second, and the time rise is very fast. It's 1 nanosecond. It's going very, very fast. It will stay on for 8 milliseconds, and then it will drop to 0 again in 1 nanosecond. So it drops very fast. And that's extremely important when you do SPICE simulation. And you have to define the derivatives at this point, right? So the derivative at this point, you can zoom in, and you're gonna see eventually that this actually will have some time. You can see it here. And you can see that it actually falls from 10 to 0 in 1 nanosecond. Right? That's extremely important because it can't jump in 0 second. Then the derivative is going to be infinite. The algorithm will diverge. So those are important things to know also when you simulate the circuit. Now what we're going to do is we're going to also plot the output, and you can see that it's acting as what we expected. It's going to take some time for it to reach the final value. It takes about 5 tau. It's about 5 tau to reach the final value. And then I added extra 3 tau, right? Like 8 tau. The total on time is 8 tau. So once you get that, you want it to estimate the time constant here. So the time constant gonna be when you reach 63% of the peak-to-peak value, right? So if you start at 0, you're gonna jump to 10. You will say that how long will it take to go 63% of the peak-to-peak value? So I can measure that using a cursor. So here is my cursor, and I can move it, right? Here is the measurements. I can move it. So over here, I'm at 16, right? At 16 when it jumps to 0, and then I'm gonna move it until it reads 63%. So I'm looking at the voltage here. I know the final value gonna be 10. 63% of that gonna be 6.3 volts. So you can see here that I started at 16 millisecond, and now I am at 16.995 millisecond. So based on the simulation here, the time constant gonna be around 0.995 millisecond, which is very close to the 1 millisecond that we're looking at. So again, there is some accuracy in the algorithms to predict the curve from here as it goes through, as well as the step size, the resolution of the graph, right? So, but this is very good. This is like really very close to the expected value that we are looking at. Basically, we have validated the time constant, which is the time required to go 63% of the peak-to-peak value. You start from 0, you end up at 10. So how long will it take to move 63% of that? The same thing happens when it falls. So if it's gonna fall from 10, it's gonna drop here to 37%. So you're gonna say 63% dropping, gonna be when it jumps from 10 to 3.7 volts. So let's see how long will it take, right? This is dropping 63%, so it's gonna be until we hit 3.7, yeah, more or less here, right? And you can see one more time that it took 1 millisecond, right? Starts at 24 here, milli, and took about 1 millisecond to drop 63%. So you can do it on the time rise, and you can do it on the time fall. That's how you can measure the time constant of the circuit. The next thing we're gonna do is we're gonna show you what happens if you apply a sine wave. So here I'm gonna come to the voltage. So let me come over here, and I'm gonna right click on the top of the voltage to change it. So I'm gonna move from V pulse to V sine, and here I'm gonna say that the amplitude gonna be 10 volts, and here I'm gonna make the frequency, so the DC offset is 0, of course. So here it's gonna be 159 point, I would say 155. That's the cutoff frequency. No delay, no theta. Theta is basically to give you that the sinusoidal decaying function is defined by the theta here. No phase shift, and we're gonna keep it running as a sine wave, so forever. So this is the components that I'm gonna enter. So that's the definition of the sine wave. So here I know that the time period of this need to be calculated. So if I would say that 159.115, and then I'll do the reciprocal of that, so I have about roughly around 6.3 millisecond for each cycle. So I need to know how many cycles I need to define. I can come on the top of this command and right click on it, and that will take me automatically to the edit command window, right? Or I can go to simulate, edit command window. That would work also. So here, if I know that it's going to be 6 milliseconds, 6.3 milliseconds for each cycle, then I'm going to say that I'm going to simulate for 63 millisecond, and here I wanted to give it about 10 cycles. Now keep in mind that sometimes you need to play with this, because things will happen as I go at different frequencies. Now what happened is, at this frequency, I know that I have 6.3 millisecond per clock cycle. I can say that I can make it 6 micro to be a good resolution. That means I have about 1,000 samples per one complete clock cycle at minimum. That's what I have, right? So you need to always play with the maximum step size and the simulation time based on what frequencies you are doing. So I'm gonna click OK. Now I'm gonna delete this. Let's run simulate again. I'm gonna plot Vn. This is my input voltage, so you can see that it's going from positive 10 to negative 10 as a sine wave. This is my output voltage, and this is at the critical frequency. So you can see that the output, the blue line is the output, happens 45 degrees after, the peak of the output happens after the peak of the input. So it is lagging 45 degrees, right? So I subtract 45 degrees because this is the critical frequency. You can measure the phase very easily. But what I wanted to do here is I wanted to measure what's the peak value of the sine wave. So I'm gonna use the cursor. I'm gonna click on this value here, this label, the voltage label for V node at node 2, and I'll move it to the peak. So sure enough, I got 7.07, which is 1 over square root of 2 times VI. and the gain here is 3 dB, right? Because when V out will be 0.707 times VI, right, or 1 over square root of 2 times VI. At this gain, you get the 3 dB frequency. Clearly, that if you wanted to measure the time difference between the two peaks, multiply that by the frequency times the 360 degrees is going to give you 45 degrees. Right? So you can also calculate the phase difference if you want it. Now what I want you to do is I wanted to apply another frequency. So we know that this is a low pass filter. So let's make the frequency lower. Like let's say that it's going to be a decade earlier, right? So we know that here we got a gain of 7. Let's say that if the frequency, so I'm going to come over here, I'm going to change the frequency to be 15.9155. So it's a decade earlier, right? The frequency is a decade earlier. It's a smaller, and I would expect the gain to be higher. Now you need to play with the transient response. So I'm gonna change the transient response here. It needs to be 10 times slower. So I'm gonna make it run for 630 milliseconds. And here the resolution can also be multiplied by a factor of 10 because it is slower. You know, make sure that you always adjust the simulation time and the maximum step size every time you change the frequency to sample at least 1,000 points. So we simulate the values here. This is the sine wave, right? It's a slower frequency. It's about 10 cycles. And you can see that the blue line, which is the output, is almost overlapping at the input, right? So a decade earlier, you can assume that the output voltage is roughly the same as the input voltage. Remember that the impedance here is much higher at lower frequency. That means this will absorb most of the voltage using the voltage divider concept. Now what I'm going to do is I'm going to make the frequency 10 times the cutoff frequency. So let's delete that. Then I'm going to come to the voltage. I'm going to change it to make it 10 times. I'll put the period here. So it's going to be 1591.55. And then I'm going to come to the simulation. I'm going to change it to run for 6.3 millisecond, and the simulation gonna be 0.6 microsecond, because now I made the frequency 10 times faster. I don't need to simulate for longer time. But there is something I want you to pay attention to when you run faster frequency, which is basically the transient effect. You will see some of the transient effect now, but maybe if we even go to a higher frequency, you will see more of that transient effect. So let's run the simulation, see what we have here. This is our input voltage, is a nice sine wave. Let's look at the output voltage. And the output voltage looks okay in terms of simulation. It's still, yeah. So in order for me to show you that, let me remove the green line. Yeah, so that's what I wanted you to see here. This is the transient effect. You see, starts at 0, goes up, and it's not as nice of a sine wave because there is some time for it to reach the final value. So when you run higher frequencies, you want to make sure that your signal did reach the steady state. So, and 10 cycles is not good enough. You need to go for more cycles. So I think for this circuit, it's around the 5 milliseconds, more or less. It's going to be symmetric. And the way you're going to know that is by seeing what's the peak value here and what's the peak value here. If it's identical, then it's symmetric. So let me show you what do I mean by that. So if I'm going to click on here, I'm going to run the peak value over here, and I will use another cursor. I will run the min value over here, and they should be almost the same. So you can see that they're almost the same, right? So it's about symmetric over here. However, early on, like if you look at this min value and this peak value, you can see that there is a big difference, right? So the peak value, which is cursor 2, is the peak value is at 1.38 volts, and the min value will be at negative 4.6. So still it's in the transient effect. In fact, that what I'm gonna do now is I will use a higher frequency to show you that. So if I'm gonna come over here, I will change the voltage to have even higher frequency. So I would say that this is gonna be even a decade higher. So it's at 15,915 hertz. And I want to run the simulation a little bit even longer. Let's say that, let's make it go for 8 milliseconds. And remember that the frequency now is faster, so I'm gonna even reduce the resolution more. So it's gonna be at 60 nano or 0.6 micro. So the resolution here going to be at 6 nano. So I'm going to run it for longer time to see that transient effect. And then I need to lower the step size because it is higher frequency. Let's close this. Save, run. Yeah, it did run fast. Okay, so let's plot the output. This will show you the transient effect. You can see the transient effect. It takes, you know, around here. So the around here you start to see that it is kind of steady, right? It's in the steady state over here. But if you go to initially, over here is the transient, right? So if you build a circuit in the lab, you will never see this transient effect, right? Because you just turn it on and it happens for the first 3 milliseconds. That's it. And all what you're gonna see in the lab is this steady state, right? And it will look as nice and pure sine wave. However, the simulation shows you that transient effect. Now it looks symmetrical. So you can see that one peak happens at 100 millivolt and the other peak happens at negative 100 millivolt. And that makes sense because 2 decades from the cutoff frequency, the gain is negative 40 dB. And negative 40 dB equals to 1 over 100. 1 over 100 is the gain. That's negative 40 dB. And if the input is 10 volt peak, then the output gonna be 10 over 100, which is 0.1. Right? So let me plot the input. And you can see that the input here will read plus 10 and negative 10, but the output will be VI over 100. So that's why the output reads from 0.1 to negative 0.1. Also, if let me zoom out, this is the transient. If you plot in the input, you can see that the input is steady. It still goes from positive 10 to negative 10 all the way through. So the input is not affected by the transient response, only the output is, which makes sense because this voltage here is a sine wave constant. Is the voltage across the capacitor will take some time until it reaches that steady state. So when you took circuit to solve for the circuit using phasors, right, using complex numbers, basically what we did is we assumed that we are in the steady state. This transient effect is ignored when you use phasors. I think this is a good time to stop here. Basically what I did is I showed you the frequency response using the AC sweep, and then I showed you what's the time constant is using the rectangular pulse, and then I applied the sine wave at different frequencies, and I was able to relate it to the frequency response that we had in the AC sweep simulation. I hope you like this video. This should be a good tutorial for you to understand the difference between those different analyses and what kind of simulation we can get from it. With that, thank you so much, and I see you in my next tutorial video.